Hi, welcome to videos on again unlock filters. So in this video we see both band pass filter and band stop filter analysis, both theory as well as simulation. This is what you have seen in the previous video. So it's a wideband band pass filter. So this is a circuit diagram, and it was supposed to have a wide bandwidth. So that's why we have selected the FP1 and FP2s too far away. If you can clearly notice here, so this is actually a combination of one high pass filter and low pass filter. If you can carefully look at this transfer function, the Bode plot of the frequency response, you can see that initially it looks like a high pass filter. In the later half, you can see it looks like a low pass filter. It's like a combination of a high pass filter and a low pass filter. So looking at the circuit, we can clearly see that this C1 and R2 will constitute a high pass filter. If you can see this cutoff frequency FP1, which corresponds to the high pass filter frequency response, is now decided by C1 and R2. That's why you can see there is a C1 and R2. Since there is a R1 which is there in series with C1, so that's also coming into picture here. So that's why the first cutoff frequency, which resembles a high pass filter, the cutoff frequency of this first pole is decided by C1 and R1 plus R2. So that's why this cutoff frequency expression, you have a C1 and R1 plus R2, of course, into 2 pi for finding out the frequency. So that's why we set this to be very low frequency. And similarly, FP2, that is the cutoff frequency of the second pole, which is due to this low pass filter action, like a low pass filter action. You can see now R1 into C2 will actually constitute a low pass filter. That's why you can see there is a C2. Since, okay, suppose if you make this short circuited, this R1 and R2 will come in series, come in parallel. That's why you can see it's R1 parallel with R2 and C2. So this C2 and this R1 are predominantly deciding what is the cutoff frequency of this, and of course since R2 is coming in parallel with that, so that is now R1 parallel with R2, and C2 will decide what is the cutoff frequency of second pole, that is the low pass filter action of your band pass filter. So this is how the band pass filter wideband has been realized. So this has got sufficient bandwidth. Okay, if you use the values of R1, R2, C1, C2, so on so we're going to have a huge bandwidth, almost 17 kilohertz will be the bandwidth. But usually for many communication applications, we want to have a narrow bandwidth. So let us see how do we get a frequency response which is narrow here. If you can see here, since the cutoff frequency, so since the bandwidth is very narrow, it's not advisable to find out what is FP1 and FP2, but okay, the values of R1, R2, what we have chosen is, so both R1, R2 are equal to 1 kilo ohms and C1, C2 is equal to 0.1. So why we select these two is so that we want to bring FP1, FP2s as close as possible. If you can clearly see in the wideband, this is FP1, this is FP2. We want to bring them as close as possible. So the best possible frequency is, one of the best possible frequencies, okay, this can be 795 Hz and this can be 3.12 kilohertz. Since these two frequencies are very close to each other, it's difficult to find their cutoff frequencies, individual cutoff frequency of high pass and low pass filter. So effectively we want to get the center frequency of this band pass filter, so which is under root of FP1 into FP2. So it is root of FP1 FP2, which happens to be exactly 1.59 kilohertz. Suppose if you select these values R0 as 1K and C1, C2 as 0.1 microfarad, we will end up with a frequency response which is narrower with maximum gain at 1.59 kilohertz. So we'll go to LT spice simulation and try to do the simulation. Okay, so this is the LT spice simulation of that narrow band pass filter. You can see we have selected R1, R2 both as 1 kilo ohm, C1, C2 is also 0.1 microfarad. So let us do the frequency response of this and try to find out what is the frequency response. You can see this is the frequency response. Now I can find out what is the center frequency. that is the frequency at which we want to get maximum gain. So that happens to be 1.59 kilohertz. You can see it's almost there at, let me just keep it at the maximum. So I'm there almost, you can see it's almost 1.65 kilohertz, which is very close to 1.59 kilohertz. So if you exactly go to top, you can find it's exactly 1.59 kilohertz. So this way, we can able to find out the center frequency of a narrow band pass filter whose center frequency is the square root of two core frequencies. One is at 795 Hz and other is at 3.12 kilohertz. So that's what we saw in this. Okay, this is what the two frequencies. Similarly, we can see the narrow band pass filter in 20 sim also. So this is a transfer function with the values of R1, R2 and C1, C2 as this. We want to get the corresponding transfer function in 20 sim. It can be edited to these values. We'll see what is the transfer function of how to edit the transfer function in 20 sim and what is the frequency response and pole 0 positions. So let me just go to okay, this is a transfer function for narrow band pass filter with the values of R1, R2 as 1 kilo ohm and C1, C2 as 0.1 microfarad. This is upon substituting those values, we'll get this as a transfer function. Let us go to 20 sim and then edit the same values. So this what is, you can see we are making it as this is 0.0001 and 0. So this actually corresponds to 1 e power minus 4 into s. So this is 1 e power minus 8, that's what is this, and this is the quotient of s square. The quotient of s is 0.3 milli. You can see this is 0.3 milli, and of course quotient of s power 0 is 1. So this is a transfer function what we have. If we apply this, we can know what is a pole 0 position. You can say this is the pole 0 position. You can exactly make out what are the position of poles and zeros. You can see one of the 0 is at the origin, one of the pole is at minus 3820, the second pole is at minus 2.61 into 10 power 4, that is 26.18 kilo radian per second is the second pole position. You can actually see the Bode plot, it has got yes, okay, this is peak which is happening at 10,000 radian per second. You can see now I can make this to move and then it will go to global maximum. I can just say fine is almost equal to 10,000 radian per second, which is exactly 2 pi into 1.59 kilohertz happens to be 10,000 radian per second. That's what we saw in the simulation also. So you might have seen that the simulation also we saw this is happening at 1.59 kilohertz. In terms of radians, it is 1.59 multiplied by 2 into pi is actually 10,000 radian per second, which is exactly seen here. So this is 10,000 radian per second for the same values of R and C what we did it for LT spice. So let us now move on to band stop filter, then try to see what is. This is band stop filter RC network. This is the one which is deciding where the poles and zeros of the band stop filter should be. So band stop filter, we'll see what is the first transfer function of band stop filter. So we are again now replacing this parallel combination by ZP and then series combination of R and C as ZS. So these are the values upon taking the Laplace transform for the capacitance. So this is ZP, this is ZS. So upon finding what is V0 by Vin, so it is equal to ZS by ZS plus ZP. So upon substituting the values of ZS and ZP and then small simplification, we'll end up with this transfer function. If you can carefully notice here, the denominator is also having a quadratic equation, the numerator is also having a quadratic equation. This clearly says that, or this clearly shows that the two poles are finite in nature and two zeros are also finite in nature. You can see initially the slope is 0, there is no pole or 0 there, so it is 0 dB per decade, and then the slope start reducing, so that is due to the location of first pole, so it is FP1. Then ultimately over here the slope almost becomes 0 dB per decade, meaning that that negative slope has become positive slope. It is due to the existence of 0. Now slope increases, there is almost 0 here, then slope again becomes 0 dB per decade, so there is a pole. So it is first pole, first 0, second 0, and then second pole. So the corresponding cutoff frequencies of two poles and two zeros are can be found using the location of can be just found looking at the transfer function. If you can clearly notice that, so this R2C2 will decide the second 0 position. You can see this is that R2C2 will decide the second 0 position. Of course, this R1C1 will decide the first 0 position. That's what is here. And similarly, FP1 is decided by R1, R2 as well as C1, C2. It is the it's not the series combination. It's actually C1 plus C2. You need to substitute the values of C1, C2 as it is, R1, R2 as it is in the equation. So upon doing this, by taking these values of R1, R2, we're going to get the first pole is at almost 16 Hertz. The second, first 0 is at 1.59 kilohertz. The second 0 is at 159 kilohertz. The second pole is at 16 megahertz. So this is the location of poles and zeros. We'll actually do the simulation with these values of R and C's in LT spice and try to see the pole positions are appropriately placed at suitable point of 16 kilohertz. This is 1.59 kilohertz. This is 159 kilohertz. This is almost 16 megahertz. We'll just see that in LT spice simulation. Okay, this is a circuit diagram of wideband band stop filter and the corresponding frequency response. You can actually find out what are the frequencies, cutoff frequencies of different poles and zeros. Let me find out what is the first pole frequency. It is supposed to be at around 15 Hertz. You can see this almost at 15 Hertz. You can see. So if I bring it down to around 3 dB down, so this is almost at, you can see now it is almost 3 dB. You can see it's at 16 Hertz. This is the first pole frequency. Second pole frequency, you can just actually see where is the second pole. I can place, this is, so this is the first 0. Let me just keep such that it is 3 dB difference is there. You can see it's almost 3 dB. The cutoff frequency is around 1.59 kilohertz. You can see you're almost there. You can see it's almost this is 1.5 kilohertz because you're almost there at 3 dB. So you can find the other cutoff frequency of other 0. It's at 159 kilohertz. You can again see this is almost at 2.9, that is almost 3 dB. You can see it's almost 161 kilohertz, which is 159 kilohertz. Okay, you can find the other pole frequency, which is at around 16 megahertz. You can see again, look at 3 dB down. You can see you're almost there. This is 15.84 megahertz. So this way we can able to locate one pole here, the first 0 here, second 0 here, and this is the second pole. Likewise, we can able to find the cutoff frequencies of different poles and zeros. So let us see the 20 sim simulation of this. Okay, upon substituting the values of R1, R2, C1, C2 onto this equation, this happens to be the transfer function. So using 20 sim, we have edited the transfer function in the same way. You can see this is the transfer function, so which has been edited. So let us see the pole 0 plot of that. So this is what the pole 0 plot of that. We can actually know the pole 0 positions. Okay, this is the pole 0 position. You can see is almost at 100. So these are the pole 0 positions, and you can also see the Bode plot of it. So this is, you can see the Bode plot. It is the first pole, first 0, second 0, and then second pole. The corresponding cutoff frequency can be easily mapped as we did it for the other filter. So this is how we can able to get 20 sim simulation for wideband stop filter. So there's a larger bandwidth for band stop filter. So this way we can able